So I'll go back. If there's only two R groups on an alkene, it's kind of simple to determine if it's cis or trans. But if it's four groups on an alkene, tetrasubstituted alkene, things become more tricky. And we started to work on that last class where we assigned priorities and we looked at the two priority groups. If the two priority groups on the alkene are on the same side, that's still a cis. And then we get a new letter, which is Z for those. And if those two priority groups are on opposite sides, we give that a trans orientation or we give the letter E. Okay, so that information becomes very important in naming alkenes. All right, we're going to try to work on those a little bit here. But what happens now in second semester of organic, we're not just limiting, or we're just not limited now to just alkenes and alkynes. Actually, we need to start to name all the remaining functional groups. All right, so we're going to watch a video that I think does a good job that starts to get us to think about how do we name alcohols, how do we name ketones, how do we name carboxylic acids and esters, how do we name amines and amides. So we need to cover the remaining functional groups in nomenclature, and that's our first immediate topic. So let me share my screen. We're going to watch the video. I'm going to review some things from the video, and then we're going to try to do some examples today in class of naming different functional groups. Okay. My computer just stopped. Okay, let me check things on my side of Teams. Can you guys see the screen?
Yes, but it's going in and out.
Yeah, but it's going in and out.
It's blinking.
Okay. Let me stop sharing. Okay, let me do this. I got this hooked up to the other screen. I'm testing the setup. Let's just do one screen right now.
You're doing construction in the math science building?
There's one of a panel fell down on Monday, so they're trying to fix it. We got some stuff going on. All right, how about now? Can you guys see my screen?
Yeah.
Yes.
Okay, good. Let's see if you guys can hear.
Chemistry with the Crash Course app available now for Android and iOS devices.
Could you guys hear that?
Mm-hmm.
Okay, let's play.
Hi, I'm Deboki Chakravarti, and welcome to Crash Course Organic Chemistry. Even when we speak the same language, we have different ways to say the same thing. Do you call a carbonated beverage a pop, soda, or just Coke? Or maybe you're looking for a drinking fountain and everyone keeps pointing you to a bubbler? Other times we're not saying what we think we mean. For example, an American asking for chips in the UK isn't going to get a bag of crispy potato circles. If they shout out for their friend Ken in Japan, people might wonder why they're yelling about a sword. Or if they're trying to say they're embarrassed in Peru with a fragmented I'm embarazada, they're actually saying they're pregnant. Language is complicated, and it can be especially confusing in the chemistry lab. If we ask our lab partner to pass the dichloromethane and they hand us a bottle labeled methylene chloride, is that the same chemical or not? To unite the scientific community, the International Union of Pure and Applied Chemistry, otherwise known as IUPAC, was established in 1919. This group wanted to make sure that chemists around the world could communicate accurately. 100 years later, IUPAC is still the guiding organization for all things nomenclature. Thanks to them, we have some standard rules for naming organic chemicals.
Okay, is it spotty for you guys, or is it smooth?
It's spotty.
Spotty. I'm looking on the iPad. It looked really spotty. I don't know if that just means I need to.
You can review content from Crash Course Organic Chemistry with the Crash Course app, available now for
All right, let this play. Give me 1 sec. Let me see if I can fix this.
Android and iOS devices.
Hi, I'm Deboki Chakravarti, and welcome to Crash Course Organic Chemistry. Even when we speak the same language, we have different ways to say the same thing. Do you call a carbonated beverage a pop, soda, or just Coke? Or maybe you're looking for a drinking fountain and everyone keeps pointing you to a bubbler? Other times we're not saying what we think we mean. For example, an American asking for chips in the UK isn't going to get a bag of crispy potato circles. If they shout out for their friend Ken in Japan, people might wonder why they're yelling about a sword. Or if they're trying to say they're embarrassed in Peru with a fragmented I'm embarazada, they're actually saying they're pregnant. Language is complicated, and it can be especially confusing in the chemistry lab. If we ask our lab partner to pass the dichloromethane and they hand us a bottle labeled methylene chloride, is that the same chemical or not? To unite the scientific community, the International Union of Pure and Applied Chemistry, otherwise known as IUPAC, was established in 1919. This group wanted to make sure that chemists around the world could communicate accurately. 100 years later, IUPAC is still the guiding organization for all things nomenclature. Thanks to them, we have some standard rules for naming organic chemicals.
Okay, this is the best I can do. I'm sorry. Take what you can from the video. We will talk about this in some detail shortly. So try to take as much information as you can. I will send a link to this as well later today.
By the time IUPAC came along with standard rules, organic chemistry as a field was already over 100 years old. Many chemicals had common names given to them by the people who discovered them based on their source or smell or color. For instance, vanillin is isolated from vanilla beans, and cinnamaldehyde is isolated from cinnamon. Alcohol, ether, acetone, and acetic acid are common names too. While some common names might sound fun, you have to memorize them. And they don't tell you much besides, like, there's a chemical responsible for the flavor in vanilla ice cream called vanillin. Not super useful for learning chemical structures. Sometimes chemists even disagreed about what each common name meant, sort of like regional differences about what to call a carbonated beverage. Despite IUPAC's best attempts to make organic chemistry nomenclature less confusing, many common names are still used today. Probably because vanillin is easier to say and put on a bottle than 4-hydroxy-3-methoxybenzaldehyde. But that longer name is a systematic name that follows a set of rules, which means anyone who knows those rules can draw the structure. There are 3 basic steps to IUPAC systematic naming. We'll add more as we discover more about organic molecules throughout this series, but for now, these will get us started. Number 1, find the longest carbon chain and give it a root name. Number 2, identify the highest priority functional group and add its suffix to the root name. And number 3, identify the types of substituents and their positions on the carbon chain. Then add a numbered prefix to the root name. So we start building any systematic name with the root name, which comes from the longest carbon chain in the molecule. The word longest is key because some molecules will have long chains sticking out that can throw you off. So make sure to do a little extra counting and make sure you actually found the longest one. Carbon chains containing up to 4 atoms have arbitrary sounding root names. 1 carbon is meth, 2 is F, 3 is prop, and 4 bute. This can be a little tricky to remember, but you can use this mnemonic to help. Monkeys eat purple bananas. For carbon chains with 5 to 12 atoms, the root names are similar to geometric shapes. For example, a pentagon in geometry is a 5-sided ring. And if a carbon compound has the word pent as its root, then it's a 5-carbon chain. A 6-carbon chain is hex, 7 is hept, 8 is oct, 9 is non, 10 is dec, 11 is undec, and 12 is dodec. If you need a root name for a carbon chain with more than 12 atoms, I don't have it memorized. There are plenty of resources out there to look them up. Chemists usually don't deal with longer chains, and there are plenty of other things to remember besides what a 56-carbon chain is called. Back to our IUPAC rules. Once we've counted our carbons and have a root name, we need to add a suffix to indicate what kind of organic molecule we're dealing with. The simplest organic molecules are hydrocarbons, which only have hydrogen and carbon atoms. There are 4 kinds of hydrocarbons: alkanes, alkenes, alkynes, and aromatics. But we'll only talk about the first 3 for now, because smelly aromatic compounds are a little more complicated. Alkanes only have single bonds between carbons. For these compounds, we take the root name and tack on a suffix ane. For example, this skeletal structure is a 6-carbon chain, so the root is hex. And because there are only single bonds, it's an alkane, and we add the suffix ane. It's hexane. Alkanes are kind of boring compared to their hydrocarbon cousins. They're low-energy couch potatoes and don't interact with many other compounds. On the other hand, alkenes and alkynes have functional groups. Remember last episode, we said that functional groups are where all the cool chemistry happens. In alkenes, the functional groups are double bonds between carbons. And in alkynes, the functional groups are triple bonds between carbons. Alkenes and alkynes can do fun reactions to make things like light-emitting polymers, which are big molecules with regions where electrons kind of move around on a racetrack that absorbs energy and emits light. But I'm getting ahead of myself. To name an alkene, we find the longest chain of carbon atoms, and it must include a double bond. If the longest carbon chain doesn't include a double bond, it's not named as an alkene. Sorry, I don't make the rules, IUPAC does. Since IUPAC rules are all about communication, we want to let people know where that double bond is on the chain. So we'll number the carbons starting on the end closest to the double bond. For the sake of consistency, we want to keep the numbers as low as possible. Then we'll take the lowest number touching the double bond, combine it with the suffix ene, and add that to the root name of our chain. For example, the longest chain in this molecule is a 5-carbon chain, so the root is tent. Because there's a double bond, we know the suffix is ene. But we also have to number the carbons. Starting from the end closest to the double bond, that's 1, 2, 3, 4, 5. And because the double bond is between carbons 1 and 2, this compound is pent-1-ene. Notice the punctuation here. We stick dashes around the number. To name alkynes, the hydrocarbons with a triple bond, we do the same thing. First, we find the longest chain of carbon atoms and pick a root name. Then we number the chain from the end closest to the triple bond to let people know where it is, and tack on the suffix "-ine". For example, an 8-carbon chain with a triple bond in the center would be called oct-4-ine. To finish the IUPAC rules, once we have a root name and suffix, we might be done if the molecule doesn't have anything fancy going on. But frequently, organic molecules have substituents, where plain old hydrogens on a carbon chain can be replaced by other carbon chains or halogen atoms like chlorine, bromine, and iodine, for example. We communicate where substituents are by adding prefixes before the root name. Plus, just like we had to count carbons for alkenes and alkynes, we need to communicate where every substituent has done its substituting. If we're dealing with an alkane where the longest carbon chain only has single bonds, we'll number the chains so that the carbon atoms with the substituents get the lowest numbers. For example, let's take our hexane from before and replace 1 hydrogen on a carbon with a CH3 group. So in this case, we have an alkane, and we want to number the longest 6-carbon chain so that the carbon with the substituent is 2, not 5. Remember, we want to keep the numbers as low as possible. The CH3 group takes the same name as a 1-carbon chain root, meth. And because this group is a substituent, it gets a new ending spelled YL. So the prefix we add is 2-methyl to communicate where and what it is. And this compound is 2-methylhexane. If the molecule is flipped over, we could start from the left and it would still be 2-methylhexane. They're the same compound, no matter if the methyl is drawn on the right or the left. If we have 2 or more of the same substituents, we add di, tri, tetra, and so on to the prefix. So if we took 2-methylhexane and added another CH3 group to a different carbon, we get 2,4-dimethylhexane. Notice the punctuation here too. The numbers are separated from each other by a comma, and are separated from the words by a dash. But there are other substituents besides carbon chains. Let's say we take our 2,4-dimethylhexane and replace a hydrogen atom on carbon 3 with a halogen like a chlorine atom. So the molecule name gets another prefix. Halogens get the ene in their name replaced with the letter O. So chlorine becomes chloro, bromine becomes bromo, and iodine becomes iodo. That means we need to tack on the prefix 3-chloro here. Lastly, when we add substituent prefixes, IUPAC rules say we need to put them in alphabetical order, and the multipliers di, tri, and tetra do not count when we're alphabetizing. So this molecule is named 3-chloro-2,4-dimethylhexane. These rules about substituent prefixes are mostly the same for alkenes and alkynes, except when it comes to numbering the chains, the double and triple bonds between carbon atoms have priority over substituents sticking out. So we start numbering the chain closest to the bonds instead of the substituent. If we take our alkene friend, pent-1-ene, and add an ethyl group, that's 2 carbons and 6 hydrogens at carbon 3, we name this 3-ethyl-pent-1-ene. Or if we put 2 methyl groups on the 2nd and 7th carbons of the alkyne oct-4-ine, meet the spectacular 2,7-dimethyl-oct-4-ine. Now that we have the basics, we can start naming any compound, even if they look kind of complicated with more than one functional group and substituent, like this molecule. But we got this. Don't worry. We have our trusty steps. Number 1, find the longest carbon chain and give it a root name. In this case, we see there's a 7-carbon chain here, so the root is hept. Number 2, identify the highest priority functional group and add its suffix to the root name. Alkenes and alkynes have equal priority when it comes to numbering, but when an alkene and alkyne tie for the lowest number, the alkene wins. We'll count from both ends to see what's up. And look, because the alkene and alkyne tie for the lowest number, the alkene wins. So we'll use the numbering where the double bond is lower. Now we have to name our double and triple bond functional groups. And the alphabetical order rule still applies here. So with the root and suffix combined, we have hept-1-ene 6-ine. Finally, number 3, identify the types of substituents and add a number prefix to the root name. In this case, there's a bromine on carbon 4 and a methyl group on carbon 3. Taking alphabetical order into account, we add 4-bromo-3-methyl before the root and suffix. And we've conquered this puzzle. It's 4-bromo-3-methyl-hept-1-ene 6-ine. It's kind of a mouthful to say, but so much more useful to chemists than if I named it debokiine or something. Now, remember that conundrum from the beginning when we asked our lab partner for dichloromethane and got a bottle of methylene chloride? Let's build those molecules. Looking at the name dichloromethane, we know from meth that this is a single carbon and ane that it's an alkane with single bonds. The dichloro tells us that we have 2 chlorine atoms connected to the only carbon, no substituent number required. That's the skeletal structure. And if we want to get all fancy with a Lewis structure, we know that carbon often makes 4 bonds, so we can add 2 hydrogen atoms to finish it off. Methylene chloride is trickier because we can't use our IUPAC rules. We just need to know that methylene is a common name for a CH2 group. Then, because chloride is in the name, we can get to the final structure by filling in the 2 open spots with chlorine. The end structure is the same, so our lab partner did know what they were doing. But calling this compound dichloromethane makes it easier for scientists to know they're talking about the same thing. In this episode, we learned that there are 3 steps to naming molecules, which include the root name, a suffix based on functional groups, and a prefix based on substituents. And we numbered the longest carbon chain by giving the highest priority functional group the lowest possible number, or whatever gives substituents the lowest possible numbers. Next time, we'll learn how to give molecules systematic names when they have functional groups with heteroatoms. Thanks for watching this episode of Crash Course Organic Chemistry. If you want to help keep all Crash Course free for everybody forever, you can join our community on Patreon.
Okay, this was good, hopefully. Let me, sorry, I got my other iPad on. It's creating too much noise. All right. So let me get into Teams, back into Teams. So I hope that was a help. Can you guys still hear me? Can you give me a show of hands? Okay, there's some hands. Good. All right, give me one more second because I gotta switch my screen again. All right, and I'm going to stop the sharing. And then reshare the screen here. Okay, can you guys confirm if you can hear and see the screen?
Yes.
Okay, great. Let me add a student. He just said that he couldn't get in. Okay, let's review really quickly nomenclature, all right? And we're going to start working on all the other functional groups, okay? So there's 4 rules that I like to kind of use to help with nomenclature: identify the parent chain, number the chain correctly, deal appropriately with substituents, and then all right. Mr. Young, you made it in out here. Okay. I'm going to mute you, Mr. Young. Okay, great. So rule 4, when it comes to naming the molecule, all right, at this point, we have all these things to do to name the molecule appropriately. We need to deal with any stereochemistry first, deal with our substituents, then give this parent root name, deal with any unsaturation. We'll talk about that here shortly. That's double bond, triple bonds, all right? And then lastly, we need the suffix for our functional groups, all right? So we'll come back to multiple, we'll come back to this. I want to jump down to functional groups really quickly. All right, we do know our suffixes hopefully for all functional groups. If not, go ahead and make a note of this in your notes, or if you're going to record this, you can record this and come back to it. And alkane has ANE as its ending or suffix. Alkene has ene, alkyne has YNE or ine. An alcohol is going to have OL, right? That might be our newest functional group so far. So whenever you see the word ol, you know that you're dealing with an alcohol functional group. All right. The ending al is dealing with aldehydes. Okay. On is dealing with ketones. Oic acid is what we use for carboxylic acids. All right, we use this O8 for esters. All right, we'll talk about here. There's something else that needs to be added with esters. We'll get into that a little bit later. All right, ether has the word as ether. All right, so if I'm dealing with dimethyl ether, we just call it dimethyl ether. All right, amines have the word amine at the end. All right, so if I'm dealing with 1-propylamine, that's the name of that molecule. All right, typically amides also does end with the word amide. So you're going to have NN2,4-dimethyl propylamide. That's typically how we name those. And nitriles also does end with the word nitrile. So you can have something called acetonitrile or methanol nitrile, right? Or ethanol nitrile. So these are the endings, all right? So you want to be familiar with these functional group endings. Now, things do change depending on what's on your substituents, but these are traditionally the functional group endings that we're going to be using for this semester, right? So let's scroll back up really quickly and talk about this. And again, we're going to do this more formally once we actually start to work in chapter 10. We're going to be making all these functional groups in 10. So we'll actually be naming the molecules once we get there. There's something now that I'm just trying to plant and seed so you guys can think about this when it comes up. What happens when you have multiple functional groups? Let's say you have an alcohol and a carboxylic acid, or you have an alcohol and an amide, or a carboxylic acid and a ketone, right? What happens, all right? There is a hierarchy of functional groups. Again, because we know that we have to end with some functional group ending, all right, there is a functional group that predominates all the others, if that makes any sense. And typically the carboxylic acid wins. So the carboxylic acid ending will always predominate if there's any other functional group. Okay, so at the bottom here is the alkane. If there's nothing else, you would end with ANE. However, if there's an alkene or an alkyne, all right, your ending would change depending on these two groups. Now, all right, if there's an alcohol present and there's an alkene, the alcohol will win. However, if there's an alcohol and an aldehyde and ketone, the aldehyde ketone wins. All right, amide will beat aldehyde and ketones. Esters will beat an amide, but the carboxylic acid will beat over all these functional groups. And we'll talk more about how to start dealing with that. So that means that we still have to name these functional groups if they're present, and the names of these things start to change. So instead of using all for an alcohol, if it's not the predominant functional group, we call it a hydroxy group now. So it's just a plain substituent. All right, again, the ketone aldehyde is losing to a carboxylic acid. This carbonyl just becomes oxo. And if the amine is losing to something else here, we just call it amino. All right, so we'll work on some of these examples here shortly. All right, so I'm gonna just draw up here really quickly. So could you guys help me name this molecule? All right, what's the name of this molecule here? How would we name this molecule? Anyone can help me out?
We gotta identify the chain first.
Okay, good. That's perfect. We need to identify the parent chain. I'm so for this to stretch out, but it's not gonna
So 1, 2, 3, 4. This gonna be 5.
Okay. Somebody says
That's
there's 5 carbons in the parent chain. Anybody else?
I say it's 6 in the longest chain.
Okay. Somebody said 6, 5. What's the numbers? What do you guys say?
6.
Okay. Show of hands if you think it's 6. Would you mind raising your hand? All right. 1 hand, 2 hand. Okay. If you think it's 5, could you raise your hand? I saw 3 hands. Okay. I got a lot of 5s. All right. As a class, can someone defend the 5, and then can someone come back and defend the 6? And then we'll make the correct answer here shortly. For those that say 6, because I asked that first, can you tell me why? Where are you seeing 6 carbons?
I saw 6 from like the beginning of the triple bond, like that was the 5, and then at the end of the triple bond, that would be 6.
Okay, so you're saying I got 1 here, 2 here, 3, 4, 5, and 6?
Yes, sir.
Okay. For those that saying 5, can you help me out?
I would say it's 5 because I go based off each point, and it's 5 points in total, and the 5th one is just basically extended. So I would say 5.
5 points. So this is a point right here. This is one of your points.
Yeah.
1. This is one of your points too.
Yeah.
And this is a point.
3,
4.
4. Then the bottom would be 5.
Right here.
Yeah.
Okay. So that happens, and this is good that we're covering it. There's actually 6 carbons here, so you guys want to remember, and it happens with triple bonds, that this is a carbon here and this is a carbon there. So if I count it again, this is 1, 2, 3, 4, 5 right here, and then 6. All right. So there's a total of 6 carbons. So this is not really a point, but because the triple bond starts here and also, I guess, is interacting here, there's 2 carbons triple bonded to each other, right? So it's tricky. So they're saying this is a carbon here, another carbon that's triple bonded to that carbon, all right? This carbon cannot be triple bonded to the one at the end, right? because this carbon is already having a double bond, and I couldn't say that this carbon is triple bonded here, right? So instead, there's a carbon here that's actually single bonded to this carbon, but triple bonded to that carbon. All right, is everybody comfortable with that so far?
Quick question.
Yes,
So
ma'am.
regarding triple bonds, is always going to be 2 carbons attached to it?
Most likely, yes. Every triple, yeah. Typically, triple bonds would be like this, unless we're drawn into an atom or to a different carbon. But when it's drawn like this, it's definitely saying that this is 1, 2, 3 carbons. That's right. Okay, good. So we got our parent chain. We know there's 6 total carbons in that chain. We need to number this chain correctly. All right, so I'm going to go this way first. So we said there's always 2 ways to number a chain, right? We can go from right to left and then left to right, if you guys are cool with that. So I'm going to do this way first. Is this the correct way to number this chain?
No.
Okay. Anybody wants to tell me why this is not the right way?
The double bond needs the lowest substantial.
That's right. Or what do you, the double bond needs to be a substituent, or?
Well, the lowest number.
Okay. When we're dealing with things that have double bonds and triple bonds, we would prefer to give those the lowest numbering if possible. Right. Let me change the color on this. So if we looked at the red, we have our double bond or a triple bond actually on carbon 1 and a double bond on carbon 3, right? If you look at I guess this teal color, our double bond starts at 3 and a triple bond starts at 5, right? So 1 and 3 is lower than 3 and 5, right? So the red would be the best numbering. Okay. So is everybody comfortable with that? All right, I'm gonna delete this one.
Yes, sir.
A teaching strategy. Very good. So what's going on? I got 2 other carbons up here, right? What do we call these things?
That's an isopropyl group.
Isopropyl group?
I mean, no. Those.
Is it 2 methyl groups?
Yeah, that's what I meant to say.
Yep, definitely 2 methyl groups. Good. Sure. If you put all this together, well, it's not really isopropyl. That'd be like a tert-butyl group. But good. Those 2 things are just 2 methyl groups. I don't want to confuse anybody, so I'm not going to say anything more than that. What do we call these 2 methyl groups? They have a special name. What do we call these things? Starts with an S.
That beautiful. I don't know.
Substituents. That's the word I'm looking for. Sorry. Good. So you guys do know that these are 2 substituents. Is everybody
Dr.
cool with?
Cooper,
Yep. Go ahead.
whenever you're numbering them, can you number and put the colors in the color that says stereochemistry, substituents, parent? Just so I know what I'm looking at.
Okay. Sure. I can put that back in the parent color. This is the parent chain. Okay, and that's substituents. Is that what you're looking for?
Yeah, that's good.
Okay, good. All right, so we got our substituents dealt with. We got our parent chain numbered. All right, are we ready to name this molecule now? We did step 1, right? Did we do step 2? We did 3?
Yes.
Okay, so any stereochemistry here?
No.
Look again.
We got the triple bond and the double bond.
Okay, so conveniently, because triple bonds are linear, there's no stereochemistry. We don't have to worry about that. Carbon 5 looks, it doesn't have just hydrogens on it, but it has 3 methyl groups. So We know that carbon 5 is not chiral as well, right? But what about carbons 3 and 4? What about these two carbons? There is stereochemistry here, right?
Yes, because it's a double bond and not a triple bond.
Exactly. So let me draw the other version of this so you guys could be convinced that there's stereochemistry. We'll name both of these shortly. All right, so what if I did this?
Wouldn't it be the same thing? The only thing that changes is the way that the double bond is.
Exactly. And I did that for that just for that reason, so that we'll be comfortable with realizing that there is stereochemistry here, right? Because these two compounds are not the same, right? They're similar. And the official name for these are geometric isomers, or you want to say, also you call these diastereomers. I don't have any room here. Let's move this over here. But there's two ways I could have drawn this molecule, and I wanted to make sure that I name the one that's drawn, right? So if we don't include that stereochemistry, it makes it very hard for us to know which molecule we're dealing with. Okay, so can you guys help me? What's the stereochemistry for the molecule on the left? What will you tell me? I'm going to use some heavy bonds here. I hope that helps. I don't know if it does. I'm just focusing around that double bond. What will you guys tell me about this molecule on the left? There's two words that we use: subscribe to orientate.
That one cis and that the other one is trans.
Okay, that's exactly what I'm looking for. It could be either cis or trans. Which version is this version on the left?
Is that trans?
Yeah, this is trans. Can everybody see how this is trans?
No, can we explain that?
Yep. I could explain it. All right. All this
Because those have the groups on the top.
I'm gonna draw in the hydrogens. Maybe that helps a little bit. So give me 1 sec. And then I would try to do it the quick and dirty way, but maybe we should do it the official way until you guys get comfortable. Okay. So last class, we mentioned that if we have a double bond, we just need to find our priority groups, right? So we're going to look at carbons 3 and carbons 4 as separate entities, right? So what is the priority group on carbon 3? This hydrogen or the carbon 2 or the triple bond? What you guys
The carbon 2 or the triple bond.
That's right, the carbon 2 or the triple bond. Make this a little bit smaller and get this circle here. So I'm going to put that in a circle if you guys are cool with that. All right, and if I look at carbon 4 as a separate entity, is it the hydrogen or the carbon 5 that's the highest priority for that?
Carbon 5.
Carbon 5, right?
Okay, Dr. Cooper, why is it carbon 5 again? Because of 3 methyl groups.
Oh no, it's just you can do it simply based off the fact that carbon versus H. So carbon has a higher atomic number than hydrogen does.
All right.
Okay, good. So I got my double bond. I'm gonna just draw another double bond. And I got a group that's large. I got my two party atoms here and there. What is that orientation across a double bond? What would we call that? Anyone?
You mean
What
like
do you mean by that?
trans?
Oh, yeah. When I say orientation, yeah. How are things oriented? Are they trans, the same side, or are they opposite sides, which is cis?
Oh, that's trans.
Yeah.
Trans.
So my largest party groups are oriented trans to one another, right? Opposite face. Right? What letter do we give trans?
E.
All right, is everybody comfortable with this version being the trans isomer?
Yeah, I look at it like how it's just how the carbons are on two different sides of each other.
Yeah,
Like if you
definitely.
like if you draw the line.
And that's the way that I see it too. Sometimes it could be trickier than this. Luckily, when there was this H's, I just saw that the two carbons were opposite each other, so I knew automatically that was trans. Yeah, that's exactly the quickest and easiest way is to kind of just look at the double bond and see how the carbon groups are oriented. Over here, however, what's going on with this one? I'm going to draw the H's in again to make sure we're comfortable with everything.
Both of them on the top.
Okay. Good. So again, if I had to look at carbon 3, you guys would tell me that the carbon 2 stuff is the biggest atom. And if I had to look at carbon 4, you would tell me that all this up top is a big atom. So again, I'm going to draw my double bond. And I'm going to draw the bonds coming out the double bond. And my largest party groups are oriented this way. So we call this orientation what type of alkene?
Z.
So this is the cis, also known as the Z isomer. All right, any questions so far on that? I got a worksheet coming you guys' way. This is just a skill that's built through practice. Right? You just practice, it becomes second nature. All right, but it's very important in naming. We do want to make sure we know if something is cis and trans. Okay, do you guys mind if I erase these circles?
You can.
That's
Can I erase them? I could put them back after we name the molecule if needed. I'll erase them for now just because I think it's a bit much to name. I'm going to erase these H's as well. Okay. Are we cool?
Mm-hmm.
Good. So we do know stereochemistry now for this molecule, and we need to describe the stereochemistry for the molecule on the left as E. All right, so let's name our molecule. We start with what first?
The chain. Yeah.
This is the order right here. This is the order right here. To name, we start with what first?
The chain. Parent chain.
Stereochemistry. All right,
Oh.
so the stereochemistry is E. So I'll put my E in front. All right, we're cool with that?
Mm-hmm.
All right, what's next? I deal with this. Sustentuants. So help me deal with the sustentuants. What do I have to say for that?
You have to say di.
All right, I do need to say di.
It would be
Five
dimethyl.
Dimethyl. Very good. Keep in mind, if you use the word di, they got to be 2 numbers. If you use the word tri, it needs to be 3 numbers. If you use 4, or I'm sorry, tetra, it needs to be 4 numbers. Okay, good. So I got my stereochemistry and I dealt with my substituents. What is the parent chain name or root name?
Hexane, hexine, I don't know.
This hex for now. All right. Now we need to deal with any unsaturation. Do we have any unsaturation?
No.
What is that again?
Yeah.
What does that part mean?
Unsaturation just means double bonds or triple bonds.
Oh, yes, we do.
Yeah.
Okay. So help me with that. What will you guys tell me for my unsaturation? Start with a double bond first, then the triple bond. So I would say 3 ene, 1 ine. You guys see that?
Yes.
Yeah. Why couldn't you do it 4 and 2?
Oh, you want to use your lowest numbering for
Right.
every double bond and triple bond. Yeah. Good question.
Is the ene always gonna go first?
Yes. Yes.
Mr. Cooper,
Mm-hmm.
regarding those, why did you drop the E at the end?
Yeah, because the E only comes once you name the function group. Good question. So if it was just an alkane, you would use ANE. And if it was just an alkene, you would use ENE. But when it's not the final functional group, you want to make sure, well, I'm going to use the E at the end of this eventually. I'm sorry. But until then, you use the first 2 letters.
Thank you.
Yep, no problem. We're gonna do some more here shortly. I'm gonna show a difference between saturation and unsaturation. I think that will complete the story. And the last thing here, is there any other functional group here outside of double bonds or triple bonds?
The methyl group.
Methyl groups are substituents, so they're not really a functional group. So the functional group is really that triple bond. So I get to put the E at the end for that. And that's the final molecule here. I didn't give myself enough room.
Why is that triple bond the only functional group?
Well, it's a triple bond and a double bond. Because I guess the functional groups for nomenclature is either alkane or alkyne, or something else, which is alcohol, aldehyde, ketone, carboxyl acid, ester, something else. So there's no alcohol here. There's no ester here. There's no carboxyl acid. It's just a triple bond or a double bond. So the triple bond is will take predominance in the naming than over the double bond.
Oh, and if it was just a double bond, it would the ene have a E at the end of it.
Exactly. That's exactly right.
All right.
So over here, this molecule is almost exactly the same, right? The only difference will be what in his name?
Z for cis at the beginning.
Exactly. So this molecule will just be called the Z version. Okay, let's work on chapter 10, which is alcohols. Down here. All right, you know what? I didn't want you to see that yet. Actually, that's a
question, Mr. Cooper.
say that one more time.
You did say unsaturation bonds are the double bonds and triple bonds, correct?
That's correct. That's correct. And that's the example that I'm working on next. Let's work on that really quickly. I want you guys to see the difference. All right, this is going to be a tricky one here, but I'm glad that I made it. We'll talk about something here shortly. All right, let's see if we can name these two molecules. Put my verses here. All right, help me out with the first molecule on the left. How do I name that molecule? I need to come up with my parent chain. How many carbons in the parent chain?
5.
Okay.
And this will be trans, correct?
Okay, maybe not.
It wouldn't be trans only because it don't got no double bond.
Okay, that's correct. No double bond, so we can't say cis or trans. And that's a good thing to keep in mind. If there's a double bond there, and again, there's a possibility of cis or trans. You guys are gonna see a potential trick question here shortly, and we're gonna figure out why it looks tricky. Okay, did I number this chain correctly?
Yeah.
Now, let's go through which way is the correct way really quickly. All right, I could have named this chain 2 ways. Which way is the correct way to number?
The red,
The one in red.
All right, can somebody tell me why?
because of the suspension, it's on the loose.
Yeah, okay, that's exactly right. All right, so red gives me 2-methyl 3 alcohol. All right. Gray also gives me 3 alcohol, but it gives me what for the methyl group? 4, right? So we want to make sure we give sustention as what? The lowest possible numbering. That's right. Good. All right, I'm going to keep that in gray just in case, but make sure you guys are thinking along those lines. All right. So I numbered the chain. I'm sorry, I identified the parent chain. I numbered the chain. I dealt with my sustentuant. You guys already told me that this thing up here is called a what? On carbon 2. What is that called?
The methyl group.
Yeah, that's a methyl group. So I'm pretty much ready to name, right? Any stereochemistry for this molecule?
No.
No stereochemistry. No RNS here and no EZ. So we're going to skip that first line. So now I move into sustentuants, and what do I say?
2 methyl.
Bingo. Then what else?
3.
What's my parent chain? Or parent group?
Pent.
Yep, pent. Unsaturation. Do I have any unsaturation here?
No.
No. So
No,
this is
sir.
going to be and for alkane. Then I do my functional group, which is 3 all. Right. So this is going to change for the next one, right? Because it looks like there's unsaturation there. But for this molecule, I'm going to put that in red because this is what I want you guys to see. When there's no unsaturation, we still have to use the word AN for alkane, right? So this molecule is called 2-methyl pentan 3 all. All right, good. Could I name this molecule over here? So my numbering is about the same, right?
Mm-hmm.
Any questions there? All right. And I got the same sustentuant, which is the methyl hanging off, right? Everybody's cool with that?
Sir.
Okay. So now I can go ahead and start working on naming this molecule. Is there any stereochemistry?
Yup. The double bond is cis. So it'll be a Z in the front.
That's what I wanted to hear. I wanted to hear something. All right. This is a trick question. And we're going to demystify this, or we're gonna determine why this is a trick question. So let's look at 3 before we go to 2. Let's look at carbon 3. If I had to ask you which group on 3 is higher priority, will you tell me the OH or this carbon, this alpha group? Which carbon has ours?
The OH.
The OH, that's right. Can you tell the class why? Why is OH higher than the alpha group?
Because the oxygen and the hydrogen got a higher atomic number than the carbon.
Dead on, that's correct. Perfect, perfect. Oxygen has an atomic number of 8. Carbon has an atomic number of 6, so this is going to win. Carbon 2, let's look at this really closely. Which carbon has priority? This methyl or that methyl?
The one on top.
2.
The one up top? Tell me why. Why is this one higher priority than that one?
Is it because it's near double bond?
No. And this is
Hold on.
this is the trick question. Whenever you have 2 H's, two methyls, 2 of the same of anything. I'm going to just call this R and R. When they're identical, there's no stereochemistry for here, right? Right?
So are you saying there's stereochemistry where the OH is, but no stereochemistry where the methyls are?
Actually, no. And so for me to even do the OH was just trying to trick you guys. I was trying to lead you into thinking there was stereochemistry. But you have to have an orientation. There has to be it needs to be a combination of effect, right? I need to have a higher priority group on side 3 and side 2 to have stereochemistry. So think about it like this. If OH is the priority group, is it cis to the higher priority group or is it trans? It's both cis and trans to the same group, which is what? A methyl group, right?
The 2 methyls.
Yep. It could be, it's trans to that methyl group, but cis to that methyl group. So can you say that this is a alkene, or can you say that this is a trans alkene?
Yes, sir.
You can't, right? There's no way you can, because it's cis, it's both cis and trans to the same group.
You basically can't compare it to nothing.
Exactly. You can't determine the orientation in space. You can't say that these 2 large groups are on the same side or the 2 large groups on the opposite sides, because this side has the same priority groups. Both trans. That's exactly correct. So in this case here, because you cannot determine if OH is cis or trans, overall this molecule has no stereochemistry. Okay? So keep that in mind. So whenever you see alkenes that have identical groups on one of the carbons, that kills the stereochemistry for the alkene. Right? So we can't say cis and trans. So this molecule isn't cis or trans. And we'll talk more about that. I got some practice problems where you guys can be identifying those scenarios as well. Okay? So here there's no stereochemistry. I'll write up here, no stereochemistry. Okay. So can we name the molecule now? So I don't have to worry about saying E or Z. I do with my substituent first. You guys told me that's a methyl group. My parent chain is pent. However, I do have a double bond now, right? So I do have unsaturation. So what should I say next? 2-ene, 3-ol. Hopefully you guys can see how things change a bit when they're.
Get the ene from again.
Okay. Give me 1 sec and I will just want to change the font here. Why is it doing this to me? All right. Open it up for me. All right. So if we look at this molecule, we do have unsaturation. So here I had no unsaturation, so I didn't have to worry about it. I just said and, tan, right? All right. And for everything is single bond. Over here, I do have a double bond, right? And how do we describe double bonds? I have to use alkene, En. So on carbon 2 is where our double bond starts. So I say pent-2-ene, then I'll say my 3-ol for the alcohol functional group. Right? So does that help?
Yes, sir.
Okay, great.
Yes, sir.
All right, let's do one more and I'll let you guys go. I should have made it easier than that. Hey, what's up? Hey. Happy New Year. Can you give me a few seconds? I'm trying to wrap up class. Thank you. If I ask you guys to name this molecule, what would we do for this one?
We got a number first.
All right, this number. This is a tricky one a little bit. I can say 1, 2, 3, 4, 5, right?
5. Yes, sir.
Let me get this out of there. Or I can go the opposite way, right?
Mm-hmm.
So which way is right?
Your first way.
Can you tell me why?
Our double bond got to be at the lowest. So at the lowest, it'll be on 1 instead of 5.
Who's that? Who's this?
Miss Summers.
Miss Summers. You was in my class last semester?
Yes, sir.
Okay, Miss Summers. That's exactly right. Even though, and I remember when I was in college, I used to get this tricked up. I never really paid attention to it like I should. All right. Even though the triple bond comes at the end, the double bond numbering predominates. All right. I still got to get the double bond, if possible, the lowest number. All right. So the correct way to number this is red, like you guys said. Right. Red is correct because the double bond has the lowest possible numbering. The alcohol is on 3 on both cases, but I need to get the double bond the lowest. All right, help me out. How do I name this molecule? Any stereochemistry here?
Yes, sir.
There is stereochemistry? Beware. What's at the end of this alkene? 2 what?
2 hydrogens.
Yep. So can I say that there's stereochemistry for this molecule?
No, it's not.
Okay, good. No stereochemistry. Help me out. Any substituents? No substituents. So I'll go right into the parent chain. What's the parent chain? Root. 5, which is pent, right?
Pent.
Do I have unsaturation? I do. So what do I say? 1, 4, ein, then 3 what? All. Go ahead. I'm sorry.
We wouldn't put the EN before the pen.
Before the pent?
Yes, sir.
No, ma'am. This is I'm using the latest IUPAC. So you want to put the number before the functional group.
Okay.
All right, I'm going to color code these if I can. Put that in red. That's unsaturation 1. That's another unsaturation, and that's my functional group. Right? Good.
Oh, so since alcohol is not necessarily like a substituent like a ethyl or a methyl, that's why you didn't put nothing in the front and you just put pent and started naming the double bond.
Exactly. Well, in this case here, the alcohol wins as the functional group, so that's why it's at the end.
Okay.
Because
And okay.
It beats
So
double bond.
put the weakest in the front.
Yes, that's right. That's exactly right. If I had a carboxylic acid or a ketone, then the alcohol would actually move as a substituent, and we would have to call it a hydroxyl group. We're going to do some examples of those shortly. In this chapter, you guys will be making we're going to be oxidizing alcohols to ketones and carboxyl acids and all that. So we're going to be working on naming all those different scenarios. Okay, good, good. This is not too bad, right? Not too bad.
Dr. Cooper, would these recordings be sent to us on Canvas, or
Yes.
we have to come?
No, I'm gonna send it. I got the other one. I didn't send it. I just had so much little things came up with my lab. I just kind of got overwhelmed with trying to get that set up. But I will get this done today. I will send you the last Tuesday's write up, and you will have this sheet as well. And then you also will have an activity sheet to work on before class Tuesday. So you guys do have a quiz that's due by 9 o'clock on Tuesday. All right, I will release that later today, if not tomorrow. So you guys have the whole weekend to work on it. And that's always going to be the case for this class. Every Tuesday morning, there's going to be something that you had to do over the weekend. All right. And again, because of that long weekend break, I don't see you guys again until Tuesday. Right. So I want to make sure you guys are doing something in that gap. Okay. How do you guys feel about that?
Do you guys have office hours? Do you have office hours?
Oh, I don't know my office hours yet. I would know later today. The only reason why I don't know, the department told us to be on alert because we might get a new class. So the schedules will be confirmed today. So once I know if I pick up a new lecture or not, I will send you guys my office hours.
Okay.
So just give me a few seconds there. For the most part, I'm going to use the attendance log. I think only one person contacted me saying they could not get in class. So let me download that and I'll use that for attendance because class is almost over. Okay, good. You guys are doing good. And I wanted to say this. Have you ever heard of a drug called Tylenol?
Yes. Yeah.
What functional groups are present in that drug? All, right? So we think it's in there. A double bond, and what else? And an alcohol for sure, right? So you guys are starting to get like how people actually come up with the names of drugs, right? You hear the word Tylenol. Why are they saying Tylenol, right? Double bonds and alcohols are present in the molecule. Okay. You heard of Pantene, right? You ever heard of Pantene shampoo?
Yeah.
Why did they call it Pantene? What's present in that shampoo? Alkenes. Right? A lot of alkenes, that's right. Good, good. All right, see you guys on Tuesday. I'm gonna stop the recording. If you need to contact me, I'm free tomorrow at the same time. I don't have a class on Friday. So if you need to chat with me, you're more welcome to contact me then.